Okay, today we will get back to derivatives of some very specific functions, namely exponential and logarithmic functions. No structural theorems today. And along the way, we will finally be able to define this mysterious number e, which you have probably met in a pre-calculus class. But if so, I'm guessing you would be hard-pressed to give a satisfactory definition of what e actually is. It's very, very hard to make sense of what e is unless you know a little bit about derivatives. Well, you do know a little bit about derivatives now, so now we should be able to do that. So let's start with exponential functions. If we have some exponential function, b to the power of x, what is its derivative? One incorrect thought that sometimes occurs to people, I'll put it here in the red thought bubble of doom, which is where bad thinking occurs, is that the derivative of b to the x might be x times b to the x minus 1. Can't we just use the power rule? No, 1,000 times no, we cannot. That is totally inadmissible here. The problem is that the power rule applies to power functions, which by definition have the form x to the b, where b is some fixed power, like x squared or x cubed or x to the 4/3 power. At any rate, the variable in a power function is the base. That's what's changing. It's the power that remains constant. This guy, on the other hand, is an example of an exponential function, a function of the form b to the x, where the exponent itself is the variable, and the base remains fixed. Despite some surface similarities, these are very different functions. All you have to do to see that is to compare simple cases like x squared, a power function, and 2 to the x, an exponential function. The power function grows moderately rapidly, but the exponential function grows, well, exponentially, explosively. Put 10 into this function and you get 100 out. Put 10 into this function and you get 1,024 out. Put 50 into this function and you get 2,500 out. Put 50 into this function and what you get out is greater than 1 billion millions. The moral of the story being that power functions and exponential functions are very different beasts. This is not a power function, and therefore we cannot use the power rule to take its derivative. Okay, so we know what the derivative is not, but what is the derivative of an exponential function with base b? Well, let's see what we can learn by going back to our recipe for computing derivatives from first principles. Let's rewrite this thing as this, a ratio of infinitesimal changes. And we remember how this works. We're making a little infinitesimal increase to the independent variable x, changing it from x to x plus dx, and we get a corresponding change in the output of the function. This will become the output of the function after the change minus the output of the function before the change. Well, after the change in input, when the input becomes x plus dx, the function's value will be b to the x plus dx. And from that, we have to subtract the value before the change, which is, of course, just b to the x. And the dx, of course, just comes along for the ride for now. Well, it's not clear what, if anything, I can do with this expression. But after a good long while staring at this thing, it might occur to you that I could break this up into two pieces, like this, just using properties of exponents, and then I've got a factor of bx in common in both terms upstairs. So I could factor that out, rewriting this numerator like this, which is sort of interesting because now I've got bx isolated as a factor of the whole thing, and yet b to the x was the function whose derivative I was trying to take in the first place. Let me actually take this bx and put that factor out here separate from the rest of the fraction so that I end up with this. Okay, a perfectly legal algebraic move, but what was the strategy behind it? The reason I did that is because the stuff left over is something that we can actually characterize geometrically. Let's think about the graph of an exponential function b to the x. We know what those look like. The graph of y equals b to the x looks like this, showing the characteristic features of exponential explosion as x increases and getting closer and closer to 0 as x goes to negative infinity. We have that asymptote right there. And of course, the point through which this is passing is, well, x is 0 here. And if we put x equals 0 in, we get b to the 0, which is 1. So the coordinates of that point are 0, 1. Oh, I'm assuming, by the way, that b is a number greater than 1. That's when we get exponential growth. If b was a number between 0 and 1, then we would have exponential decay going the other way. The argument works there as well, but I'll just stick to this one case to give you the idea of what's going on. And my claim was that this stuff in the parentheses could be understood geometrically, and we will understand it in terms of this picture. The 1 in this expression I'm going to relate to this 1 right here, the y-intercept of this graph. In fact, let's imagine zooming in on a little infinitesimal neighborhood of that point. Blowing this thing up to enormous scale, of course, we see that locally, in the infinitesimal neighborhood of that point, the curve is a straight line. Once again, that is our key geometric insight to all of differential calculus. Locally, curves are straight. Well, if we were to move over to the right infinitesimally by dx, and then we moved back up until we got onto the tangent line, which is the curve itself on this scale, what would this infinitesimal change in y be? I don't mean dy, I mean in terms of x. Well, the easiest way to see that might be to think about what the coordinates of this point right here would be, because this change in y, of course, would be its second coordinate minus the second coordinate of this point, which is 1. Well, that should be pretty easy to figure out. The first coordinate of this point is 0, because of course it is just this point right here. We're starting where x is 0. And the second coordinate of this point, we said, is 1, simply because this is the graph of b to the x. And of course, b to the 0 is 1. All right, fine. Let's think about this point. What's its x-coordinate? Well, it's dx to the right of 0. So this is going to be where x is dx, which means the first coordinate of that point would be this infinitesimal dx. And therefore its second coordinate would be, since it lies on this line, which is this curve, whose equation is y equals b to the x. So this relationship is satisfied by the y-coordinate and x-coordinate of any point on it. This second coordinate must be b to the power of dx, like so. And now I can just read this change in y off of my two coordinates. It's going to be the value of y after the change minus the value of y before the change. Thus, this will be b to the dx minus 1. Now I have expressions for the change in x and the corresponding infinitesimal change in y. And that means I can tell you the slope of this line. In other words, the slope of this curve as it passes through the vertical axis. So the local slope is going to be the rise, b to the dx minus 1, over the run, dx. And lo and behold, this is precisely the expression we have in our parentheses there. So let us make use of this equality to replace this ugly-looking algebraic expression with something with geometric content that we can grasp tangibly. So in place of all this stuff, I'm going to put the local slope of y equals b to the x at 0, 1, the point where the curve crosses the vertical axis. And now we have discovered something interesting. Let me clean up some of this clutter and these intermediate steps before we discuss it further. We have discovered that the derivative of b to the x, that exponential function, is some constant multiple of itself. And the constant in particular is whatever the local slope of the curve is as it passes through the vertical axis. So to take a few examples, the derivative of 2 to the x is some constant multiple of 2 to the x. And what is that constant multiple? Well, if we had our graph of y equals 2 to the x, whatever the slope of that tangent line is there, that slope would be this value right there. Don't be so foolish as to try to estimate it from my bad drawing. Obviously, this isn't to scale. But you get the idea. If this slope were, let's say, 0.7, then we would get 0.7 in there. If this slope were 1.5, then we would get 1.5 in there. And similarly, the derivative of 3 to the x, that exponential function. I don't know exactly what it's going to be, but I know what form it's going to take. It will definitely have the form some constant multiple of 3 to the x, because the derivative of any exponential function is a constant multiple of itself. And as we've said, the specific constant multiple is the local slope of the curve as it passes through the vertical axis. So if we were to draw the graph of y equals 3 to the x, well, again, putting up with my lousy drawings, one thing we do know is that 2 to the x grows very fast, but 3 to the x grows even faster, like this. And so since this constant would be the slope of this blue curve as it crosses the vertical axis, well, whatever that slope is, it's bigger than the slope was here. So whatever number we had here, this number would be bigger still. And you get the idea. If we were to look at the derivative of 5 to the x, well, we've already determined that it's going to be some constant multiple of 5 to the x. And that constant multiple will be the slope of 5 to the x as it crosses through the vertical axis. And so on for any exponential function whatsoever. And once again, if 2 to the x, the black curve, grows very rapidly, and 3 to the x, the blue curve, grows more rapidly still, then 5 to the x, this purple curve, grows even more rapidly, which means that the slope as it passes through the vertical axis would be even greater, which means that this constant, whatever it is, would be greater than this constant, which is greater than this constant. But in all cases, the derivative of an exponential function is a constant multiple of itself, and the constant in question is the local slope of the curve as it crosses through the vertical axis. Okay, I've made a little animation on GeoGebra that I hope will reinforce this point, since there's only so much you're going to get out of my crude drawings. Let's bring in a little more accuracy. And in fact, while we're over there, we can get a pretty good approximation as to what these three constants will actually be. Okay, here's a more accurate picture of the last exponential function we were looking at, 5 to the x. And as you can see, its slope is about 1.61. So if I go back to our work before, I could fill that value in. The derivative of 5 to the x is going to be approximately 1.61 times 5 to the x. Now, it's an approximation because I'm just reading something off of a graph, but this gives us a sense of what's going on. Now we could do the same thing for 3 to the x and 2 to the x, which I'll do now. Okay, I have set this thing up so that I can change the function's base. That's what this slider here is doing. So by pushing this down, I can change the base. I'm reducing the base, and you can see the curve kind of slackening out like that. So I can find different things, like we were looking for 3 to the x. When I get down to 3 to the x, the slope is about 1.1, just a bit over 1. And if I go down to 2 to the x, the slope is about 0.69. So let me record those in our work on the other page. We found that our derivative of 2 to the x is about 0.69 of 2 to the x, while our derivative of 3 to the x is about 1.1 times 3 to the x. The crucial thing being, once again, that the derivative of an exponential function is the exponential function itself times some constant of proportionality, and that constant of proportionality is the slope of the curve as it crosses through the vertical axis. I know I'm repeating myself, but I want that point to sink in. Now these three constants that we found, they're all awkward sorts of numbers. What is the nicest kind of number that we might imagine being here? I mean, you might say a whole number would be nice, but there's one whole number in particular that would be very nice, namely 1. If we were so lucky as to find a particular base b for which the local slope as it passes through the vertical axis is 1, well, we would have something pretty remarkable, because then we would have that the derivative of b to the x, whatever that b would be some constant multiple of b to the x, and that constant multiple would be 1. That means that the derivative of b to the x for that special base would just be b to the x. It would be a function whose derivative is itself. Well, in fact, it's clear that there must be some special base b with that property. Because after all, when the base is 2, then the slope is 0.69, which is below 1. And when the base is 3, the slope is 1.1, which is above 1. So at some point, as the base changes from 2 to 3, somewhere in between 2 and 3, the slope must go to 1, because it has to pass through 1 as it goes from 0.69 to 1.1. So there is some magic base somewhere between 2 and 3 that does the job. We'll discover more about its numerical value in a moment, but I want to stop here and make a definition. E is the base of the unique exponential function whose slope, as it passes through the vertical axis, is 1. So we know that such a base exists. We have decided to call it E. We could have called it something else. We could have called it zeta or q, but we didn't. We call it E. And right now, all we know about E is that it's some number between 2 and 3. But whatever it is, we know something very important about the function e to the x. A consequence of this definition is that e to the x is its own derivative. Be sure you understand this argument, because that's what it takes to really grasp what this number e is about. It's not quite so simple as the definition of pi, but in comparison with that one, pi, we said in the first lecture, was the ratio of the circumference to diameter in any circle. That's a constant because of the similarity of all circles. And then we could ask the question, well, what's the numerical value of pi? And there are various ways of showing. First, that it's a little bigger than 3. Second, that it's about 3.14. And then you can get increasing accuracy as you want. But we've answered the first question here. What is e? Well, I've given you the definition. It's the base of the unique exponential function whose slope as it passes through the vertical axis is 1. Now, what's the numerical value of e? If I wanted to say e is approximately equal to some number, we know that it's bigger than 2 and smaller than 3. Can we say more than that? We can squeeze a little more information out of that GeoGebra graph. Okay, the slope is 0.69 for y equals 2 to the x, and when we get to 3 to the x, we said it's going to be 1.1. So it's somewhere in between that. So let's just go down a little bit until we get the slope is as close to 1 as we can get. So it's somewhere between 2.75, the base is somewhere between 2.75 and 2.7. So that tells us at least the value of e to 1 decimal place. E is bigger than 2.7, but it's smaller than 2.75. And as long as you know that e is about 2.7, that's about all you really need to know. As with pi, you can get better and better accuracy. And again, as with pi, it turns out that e is an irrational number. So you'll have to settle for numerical approximations. You're not going to be able to write it as a fraction or something like that. And actually, if you look at the decimal expansion of e, it begins in kind of a funny way, because it almost looks like it's going to repeat right at the beginning, because it's 2.718281828. You might think it's going to go on repeating itself from there, but it doesn't. The next digit is 4. But as I say, you should know at least that it is 2.7. Many people know at least that it's 2.718. But the fact that e is about 2.7 is something we just saw with our own eyes. In the homework, in the book, I have written an exercise that will help you approximate e to much greater accuracy than that, and without depending on computer software. If I have time at the end of this video, maybe I will say a few words about that here. But for now, I hope you can at least bask in the understanding of what e is. And this statement right here is definitely the easiest derivative of all of those you should have in your head. No one ever forgets what the derivative of e to the x is. But come back to these earlier exponential functions, like 2 to the x, 3 to the x, and 5 to the x. We left those in a somewhat unsatisfactory state, with these approximate answers, where these constants were things I had to read off of a computer. That's not satisfying at all. I would like to know what the derivatives of these functions are, in an exact sense. I mean, I know that the constants are going to be the local slopes of the curves as they run through the vertical axis, but I would like an actual algebraic expression for this. It's going to be some algebraic expression times b to the x. What will that be? And of course, without dx's, without any infinitesimals. In the end, I want to be able to say the derivative of b to the x, this real function, is some other real function without any infinitesimals expressed in there. Because the infinitesimals are like scaffolding, very useful scaffolding. They help us build something. But if they're still around at the end, then the building isn't quite complete. Anyway, this is the next task we will turn to. Finding an algebraic expression for the derivative of b to the x, where b is any old base, not just e. But e is actually going to help us accomplish this. I want to remind you that e is most commonly encountered, perhaps, as a base for a logarithm, namely the so-called natural logarithm, which is usually written ln of x. This is just a logarithm whose base is e. It's the power we have to raise e to get x. It's therefore the inverse of the function e to the x. By the way, if we were to draw e to the x, the exponential function on here, of course it would fit between 2 to the x and 3 to the x, something like that. And its inverse function is the natural logarithm of x. Anyway, I mention this because we will need it in figuring out an algebraic expression for the derivative of b to the x in general. Let's do that now. The question is, if y is b to the x, what is dy dx? And our solution is a pretty clever one, and actually a pretty common one when it comes to exponential functions. As you probably saw in a pre-calculus class, you can take any exponential function and twist it around a bit so that you end up expressing it in terms of e. The trick is just to rewrite the base so that e is in there. Now, how do I rewrite b in terms of e? Like this. You should see why the two blue expressions are equal. The exponential function e to the x and the natural logarithm are inverses of one another, so that this all simplifies just to b. Or just remind yourself of what this all means. The logarithm of b is the power we have to raise e to get b. So we are raising e to the power we have to raise e to get b. So of course we get b, and these two expressions are equal. But this looks much more complicated. Why will this help us? Well, you'll see. First, I can just use an exponent property to combine the exponents, so this won't be so messy. And we end up with e to the log b times x. Now remember, b is just some number, and this is the logarithm of that number. So all this stuff in parentheses, that's just some number. So this is e raised to some constant multiple of x. If it was just e to the x, I would know how to take the derivative, because I know the derivative of e to the x is e to the x. But it's e to something times x. Well, this is a composition of two functions. There's a linear function, where the input is just multiplied by a constant, and then we run the result through the exponential function. Well, we have seen a trick that allows us to take derivatives of composite functions. It's that old chain rule trick. We can resolve this by introducing an intermediate variable, u. Let's just rewrite this way. This is e to the u, where u is the natural logarithm of b times x. So u is a linear function, and we have that sitting inside this exponential function. And once we've written it this way, y is e to the u, where u is something else, I should be able to take the derivative easily, because I know how to take the derivative of e to the something, and I know how to take the derivative of linear functions. So let's get to work. Thus dy dx is, we're going to use our little factoring trick, dy du times du dx. This equal sign holds because the du's cancel, and now we just need the various pieces. dy du, derivative of y with respect to u. Well, y is e to the u. Well, the derivative of e to the u with respect to u is, of course, e to the u. That's our property of the exponential function. And then the second factor, derivative of u with respect to x. Well, here's u as a function of x. It's a linear function. Log of b is not a function. That's just a constant. And it's that constant times x. If this were u equals 3x, the derivative with respect to x would be 3. If this were u equals 42x, the derivative with respect to x would be 42. Well, it's actually u equals log of b x, and log of b is just a constant. It's not a function of x, so the derivative with respect to x is just log of b. This is a good start, but we need to put everything in terms of x, and I still have this u there. Well, to get rid of it, I just go up to my little ux dictionary right here and make the appropriate substitution, which means this turns into this. In place of u, I have log b times x, and I can now unpack this by using that same exponent property I used a few moments ago, but in reverse. I can rewrite this as e to the log b to the power of x, because of course this simplifies by multiplying those two, which is what we had before, and the log b just sits there. But now look at the stuff in the parentheses. What's that? Again, the exponential function and the natural logarithm function are inverses. Spell it out in your mind. We're raising e to the power you have to raise e to get b. So of course we end up with b. Let me just swap the order there, and we have it. If we start with y equals b to the x, then we found that the derivative of that thing is log of b to the x. And this fits in nicely with what we discovered before, that the derivative of an exponential function is a multiple of itself, a constant multiple of itself. And now we see what that constant multiple is. It's the natural logarithm of the base. So let's put this result over here. The derivative of the exponential function b to the x is a constant multiple of the exponential function itself, and that constant is, in fact, the natural logarithm of the base. And as always, don't just memorize the result. Really try to understand where it came from. We got this in several stages. First, we demonstrated that the derivative of any exponential function must be some constant multiple of itself. And in particular, we were able to characterize that constant multiple geometrically. We were able to say that it was the slope of the graph of y equals b to the x as it crosses through the vertical axis. Considerations of that fact led us to define this number e so that it had the property that the derivative of e to the x is e to the x. And we were able to use that, combined with the chain rule, to then come back to the original statement and figure out that the derivative of b to the x is a constant multiple of itself, and that that constant multiple, which we had already characterized geometrically, can be characterized algebraically as well, as the natural logarithm of the base of the function. So now we understand it from several directions at once, both geometrically and algebraically. And the appearance of this natural logarithm, even when the function itself has nothing to do with e, gives a good demonstration of how this number e insinuates itself in mathematics. It really does show up all over the place. But let's look at a few examples in which we'll put this idea to use. What's the derivative of the exponential function 2 to the x? Well, we know how this works. The derivative of an exponential function is a constant multiple of that exponential function, and that constant is the natural logarithm of its base, so log 2 in this case. Well, earlier in this lecture, by playing around with GeoGebra and the geometric characterization of this constant, we saw that this derivative should be approximately equal to 0.69 times 2 to the x. And indeed, if you run logarithm of 2 through your calculator, you will see that it is about 0.69. Similarly, if we were looking for the derivative of 5.2 to the x, we would know once again that this is going to be the exponential function itself multiplied by the logarithm of 5.2. And one more example, the derivative of e to the x. Well, of course, we all know this is going to be e to the x, but suppose you didn't know that, and you only knew this general recipe right here. Then you would say, derivative of an exponential function. That's going to be a constant multiple of that exponential function. And I know that constant multiple is the logarithm of the base, so logarithm of e. And what is the logarithm of e? Well, that's 1. If you are rusty on this, just spell it out in your mind. What does this mean? This is the power we have to raise e to get e. Well, obviously, that is 1, since e to the 1 is e. Rewriting that more cleanly, we have this, which is our old familiar result. Okay, we have now succeeded in figuring out how to take the derivatives of exponential functions, and on the way, we have discussed what this number e is, but we haven't discussed how to take the derivative of a logarithm. We will turn to that now. So our new question is, if y is the natural logarithm of x, what is its derivative? What is dy dx? This will be quite easy to figure out, because as it turns out, once we know the derivative of a function, it's usually pretty easy to figure out the derivative of its inverse function. The trick we use for passing from one to the other is really quite clever. The trick will work here because we already know the derivative of the inverse to this function. The inverse to the natural logarithm is the exponential function e to the x. Those two functions undo one another, and we already know that the derivative of e to the x is e to the x. Okay, so how does this help us? We're starting with this relationship y is the natural logarithm of x. What I want to do is invert this relationship so that we write x as a function of y. Recall how we do this. We've got an equation here. We're going to do the same thing to both sides in such a way that we'll end up with just x on this side. Well, how do I get just x on this side? I have to undo the action of this natural logarithm. In other words, I have to apply the exponential function to this side, which means I also have to apply the exponential function to that side to maintain the equality. And when I do that, we're going to get e to the y is equal to e to the log x. Now I made this move so that this stuff on the right would be equal to just plain old x. Talk your way through to make sure you understand why this is so. You're raising e to the power you have to raise e to get x. Well, if you raise e to the power you have to raise e to get x, obviously you get x. And now I'm just going to reverse the sides here to write it as x equals e to the y. These are in fact equivalent statements, so we could even make that a double-headed arrow. You go from here to here or here to here. Anyway, this is just another way of expressing this relationship. It helps me because this sets us up for the clever trick I mentioned. I'm trying to find dy dx in this relationship. Well, what I'm going to do is look at this version of it and find dx dy, and then I'll just take reciprocals, because the reciprocal of dx dy is obviously dy dx. So anyway, taking each side's derivative with respect to y gives us dx dy on the left side, and on the right side, the derivative with respect to y of e to the y is, of course, e to the y. Now, taking reciprocals of each side yields, well, on the left-hand side, the reciprocal of dx dy is, of course, dy dx, and on the right-hand side, the reciprocal of e to the y is just 1 over e to the y. So we've made good progress. We're looking for dy dx, and indeed I have an expression for dy dx. The only problem is that it's in terms of the wrong variable, y. How do we fix this? Well, very easily. I can fix this because up here I know how y and x are related. I can substitute that in for y, and instead of 1 over e to the y, we'll write this as 1 over e to the logarithm of x. What's e to the logarithm of x? Well, we're raising e to the power you have to raise e to get x. So of course what we get is x. And now we have this derivative in as simple a form as we could possibly hope. we have found that if y is the logarithm of x, then the derivative of y with respect to x is the reciprocal function. Let me summarize that over here. The derivative of the natural logarithm of x is the reciprocal function, 1 over x. This is a very important fact, and sort of a surprising one, that a function as sophisticated as the natural logarithm of x should be connected through the derivative to a function as simple as the reciprocal function. Anyway, these are 3 more facts to get firmly in your head. Oh, and by the way, you may wonder, what about the derivative of other logarithmic functions? What I would call unnatural logarithms, where the base is not e. What if we wanted the derivative of the base 10 logarithm? Well, fear not, you'll get to answer this question on your own, because there is a homework problem asking just that. It's an easy one to answer if you understood this argument right here, because you just repeat that argument, making the appropriate changes. Instead of having the natural logarithm here, you would have instead the base 10 logarithm. And when you invert this to solve for x, you would isolate x on one side, not by applying the e to the whatever function to both sides, but by applying the 10 to the whatever exponential function to both sides. Because 10 to this power is 10 to the power you have to raise 10 to get x. So of course you get x. 10 to this power would just give you 10 to the y. I'll leave the rest of the details to you, though I do want you to solve it as a homework problem. The truth of the matter is, in any context where calculus appears, we always arrange it so that our exponential functions have base e and that our logarithmic functions have base e, because e is the natural base of these things for calculus, because we get these clean expressions. Whereas if we use other bases, we end up with these constants trailing us everywhere. And those constants themselves are in terms of the natural logarithm. So e shows up whether you like it or not. When we discuss the chain rule further in the next lecture, I'll try to remember to do some examples where we take an unnatural base, like b to the x, and rewrite it in terms of e, so you can see what I'm talking about. The trick we used here for getting a function's derivative from its inverse function's derivative can also be used to get the derivatives of the inverse trig functions. And so I have those as exercises in the book as well, namely coming up with the derivatives of arcsine, arccosine, and arctangent. Each one of those derivatives can be obtained in the same sort of way by which we found the derivative of the logarithm. The arguments are a little trickier, especially for arcsine and arccosine, but it's the same basic strategy. I will leave the exercises to you, but I will note the results right here, because I'm likely to use them later in this series of videos. Remember, the videos are just supplements to the book. The book is where you get the complete course. Anyway, the derivative of arcsine x turns out to be 1 over square root of 1 minus x squared, which takes a few minutes to actually memorize, but that's okay. All the results you learned here are very, very easy to remember, so no harm having one that takes a little effort. The derivative of arccosine is actually very, very similar to this one. In fact, it's literally the same thing, except that there's a negative there. And finally, the derivative of arctangent x turns out to be 1 over 1 plus x squared. Again, kind of like this one, there's something sort of eerie about that. Here you have a pretty sophisticated function, arctangent of x, and its derivative turns it into this rational function, just the reciprocal of a quadratic. These, and especially this last one, have some remarkable consequences that we will see in the third quarter of this calculus course, when we get to the subject of Taylor series. Namely, we'll see that if we start with the number 1, and then subtract off a third, and then add on a fifth, and then subtract off a seventh, and then add on a ninth, and then subtract off an 11th, and then add on, well, you get the idea, and never stop. Take infinitely many terms, which is a strange idea I know to begin with, and then multiply the result of that infinite sum by 4, you will end up with pi. What? How does that work? It's in chapter 7 of the book, and we're still in chapter 2. But it's not that far away, just a little over 100 pages away in the book. But there's a lot you have to learn in the interim before you can understand why this is so, or even really what this means. So I'll erase it for now. Just a hint that these abstruse-seeming things have interesting consequences. I should also note that in the exercises, I actually sketch out 2 ways to prove these 3 facts. One is by using the same kind of argument that we used to get this, and the other way is geometric, going back to the kinds of arguments we used to find the derivatives of sine and cosine several lectures ago. So, once again, you can see things in an algebraic sense, you can see things in a geometric sense. The more angles you have into something, the more insight you have into something. And also in the exercises, I show you how you can actually get a better numerical approximation to E rather than just saying that it's got to be around 2.7 based on pictures we got from a computer graph. Do I have time to say a few words about that here? Well, let's see. Think about the graph of y equals e to the x. Think more specifically about what's going on right here where it crosses the vertical axis. Take an infinitesimal neighborhood of that point and blow it up, like so. Now if we go over dx, like this, from that point, and then go back up onto the curve to this point, well, the first coordinate of this point was 0, and we've moved over dx, so the first coordinate of this point is dx. As for its second coordinate, well, this point lies on this curve, whose equation is y equals e to the x. So that means its y coordinate has to be e to its first coordinate. In other words, e to the power of dx. Which means this side of this little infinitesimal right triangle, measuring the infinitesimal change in y, is this value minus this value. In other words, e to the dx minus 1. And now what I want to do is the oldest trick in the mathematical book. Express the same thing two different ways. The underlying thing I'm interested in here is the slope of this line. What do I know about the slope of that line? In other words, the local slope of the exponential function as it crosses through the vertical axis. What do I know about it? On the one hand, I can read it off this picture. The slope of this line is going to be e to the dx minus 1 over dx. That's just the rise over the run. But on the other hand, what else do I know about the slope of this line? Well, it's the slope of this curve as it crosses through the vertical axis. What is this curve? This is y equals e to the x. What is this e? Aha! E is the base of the exponential function whose slope as it passes through the vertical axis is 1. So that means this thing, which represents the slope, must be equal to 1. This equality holds because these are two different expressions for the same underlying geometric thing, the slope of this line. From this equation, I can extract some good information. What I want to do is solve for e. When I do that, I'm going to get that e is 1 plus dx to the power of 1 over dx. A strange looking expression, and of course we want to write this in such a way that the infinitesimals disappear. They guide us right up to the end, and then they gracefully vanish. I'll actually remove them quickly by surrendering the equality for a mere approximation. After all, we are trying to come up with a numerical approximation for e, so approximations are going to be fine here. How do I turn this exact expression into an approximation? Well, instead of infinitesimal dx, I just consider very, very small real dx's. So I'll replace those dx's with delta x, meaning a small real x instead of an infinitesimal one. When I do that, this expression becomes e is approximately equal to 1 plus delta x, all of that raised to the power of 1 over delta x, where delta x is a small but real number. And the smaller delta x becomes, the more closely it resembles an infinitesimal, and therefore the better this approximation comes. Well, delta x still looks a little more mysterious than it needs to. If I want really small real numbers, and I think of things like a millionth or a billionth or a trillionth or whatever, I tend to think of things like 1 over a huge natural number. The natural numbers we like best because we learned those when we were so small. Nobody feels confused by those. So for our small real number delta x, let's just replace delta x, a small real number, by 1 over n, where n is a large whole number, like this. So e is approximately this strange expression, where n is a large whole number. The larger n is, the better this approximation becomes. And of course I can clean this up a little bit, because 1 over n is disgusting, and as everybody knows, the reciprocal of 1 over n is just n. And now we have a famous expression for e. So famous that I'll put it in its own purple, royal purple box. And now, if you want an approximation for e, all you have to do is stick in a large whole number for n. For example, you can check on your calculator that if you stick in, say, 1,000,000 for n, which is a fairly modest large number, you end up with E being about 2.71828, which is accurate to 5 decimal places. And again, that's just with a very modest large number like a million. With larger numbers still, you can get better approximations, but 5 decimal places really is as good as you're going to need. Anyway, such is my hasty explanation for where this famous approximation comes from and how you can use it to approximate E. You can play with it more at your leisure. And that is a good place to stop. This one has been a pretty long lecture, but we've covered a lot of good ground. Next time, we will be back talking about the chain rule in greater detail than we have thus far, and you will get to know it very, very well indeed, to the point where you can use it automatically without even thinking. So farewell until then, and do those homework exercises. Bye.